Hello, good day. You're welcome to this class. I will go as slowly as possible, knowing that you may be kind of rusty when it comes to mathematics. We are going to be looking at a very important topic today, which is matrices, matrices, and vectors. Matrices and vectors. I'm sorry about that. I think I may have to clear the screen. So now let me start again. Let me define my border. Okay, matrices. All right, matrices and vectors. So that's the topic that we are going to be looking at least maybe for the next 30 minutes. We should be able to get a grip of what matrices, the relationship between matrices and vectors. I'm sure you've heard of the two together before. And this is a time for you to really understand what they are talking about and the relationship between the two of them. So let's start with the definition of matrices. Definitions. Matrices. All right. So matrices is an array of numbers or functions in rectangular form. Okay. An array. It is an array. Array, of course, comes from the word arrangement. It's the array of numbers or functions in rectangular form. In rectangular form. So it's like you put numbers in a box, in a rectangular box, or you put functions in a rectangular box. So we're going to look at, let's look at this example. Say here. So that's the box you have defined using those I think parentheses or brackets. Those are brackets. The curving one, I think those are the parentheses. So this is 1, 2, 1, 5, 0, 1, 3, 2, 1. So you have put those numbers in that box, and meaning that you have actually defined a matrix from those numbers. So you can also have it filled with a function. Okay, this is the first example. So the second example, example B, we can have something like this, something cute like this, where we have a 3x squared as a function there. Here we have 4x cubed. Here we have the exponential of x, and here we have 4x. All right, that is also a matrix. That's also a matrix. Now, it's not impossible for us to have a matrix that will look like this. Please note this particular one is extremely important for this course. We have 1, 2, 4. You know, that's another matrix. Then you can have one like this. Sorry. You can have one like this with 1, 6, 3. Okay, that's another matrix. Okay, so let's define some the way matrices are represented. Let's define a particular one. So we now go to what we call the dimension of matrices. The dimension of matrices. Okay, so now I'm going to create a big matrix here. Okay, I hope that is big enough. I'm going to write this one as 1, 2, 3, 3, 1, 0, 1, 1, 5. Okay, so you can see that we have this. We call those the rows. Those are the rows. They are the horizontally placed numbers. So this one, we have row 1, we have row 2, and we have row 3. Okay, then we have the vertically placed numbers. So those are columns. So if you look at it, they are standing. So those are columns. So we call this one C1, C2, C3. That is column 1, column 2, and column 3. So the way matrices are described, if you look at this, let me pick a color to lighten this thing up a little. If you look at this particular, oh, I thought the color didn't pick, the picker. Okay, I think, yeah. So if you look at this now, 3, you can see it's on row 1 and column 3. So this matrix here is actually, this particular matrix is actually in the row 1 and column 3. So we will call it, we can say it is A, irrespective of what is there, row 1, column 3. So if you see that, you know that that is talking about that particular matrix in row 1 and column 3. If you look at this particular one that is here, okay, you see that is in row 2 and in column 2. So we call this one, let's say it's A as well, and it's 2, 2. You can see that index, because of the index, this one has 1 and 3, so it is unique. I mean, it is different from this one that has 2, 2, even though both of them are answering A. The A is just a marker, but what actually distinguishes these matrices, that should be the indexes. So we can see this is 1 and 3. Okay, as a test to you, this particular 3, what will it be? All right, what would that one be? What will be the dimension? I mean the location of that particular element. So the things. Okay, I think I can clear the. I can save the screen now. Okay, so now having done that, let's now talk about. So we'll go back to this matrix again. I think I would prefer to be using this red marker henceforth. So we have this one. Let's say this is a 2, 3, 4, 2, 1, 5. This is a matrix. So what kind of matrix is this? You name a matrix by the number of rows and columns it has. Like this one now has a column 1, column 2, sorry, row 1, row 1, row 2, and row 3. Meanwhile, it has a column 1 and column 2. So it has a 3 rows and 2 columns. So we call this particular one, let's say this matrix is A. Let's say it is A. So we say that A is a 3 by 2 matrix. It's a 3 by 2 matrix because it has 3 rows and 2 columns. Now, note that you put the rows first, then you put the columns. So you don't put it as column row. No, it is row column. All right, it is row column. Let me see if you are following what I'm saying. What is the position of 5 in the matrix A? What is the position of element 5? Okay, All right. So that said, we can also, so we have had a gentle introduction to um, matrices. We can now continue. Uh, we can now continue. There are some other parts of matrices that we would need to talk about. Very interesting part of it. And let's talk about some special matrices. Some special matrices. When the time comes, I would explain what these matrices are actually used for. We will get there in this particular uh, class or even subsequent classes. So, special matrices. So, we have the zero matrix. Zero matrix. As the name implies, every element in this zero matrix, let's say A is a zero matrix, every element in it, sorry, 0, 0, 0, is a zero. Only zeros are contained in the zero matrix. Now, if I may ask something we've done before, what is the dimension of A? Okay, quiz. So you will I will continue to ask these questions. What, just to make sure that you are with me, what is the dimension of A? All right, that is, check the rows and columns and tell us what the dimension of A is. All right, so that is that about zero matrix. It is a very important matrix. When you are doing group theory, you need the zero matrix to find the additive identity of uh, of uh, of a matrix. I mean, of a matrix space. If you want to check if it's a group or not. All right. So we'll talk about that later if the time permits. But then now let's look at square matrix. So what's the meaning of square? Normally, you see the way mathematics name stuff, it picks this naming from English. So when they talk about when mathematics names something, then it's usually what it sounds like in English language. What's the meaning of a square? Of course, a square would have all the sides to be the same length, right? So when we talk about square matrix, then you should be able to guess what a square matrix is. All right, a square matrix. That's okay. Let's say this is A again, and it has a 2, 4, 6, 8, 7, 1, 5, 0, 8. Okay. Well, if you look at that, that's a 3 by 3 matrix because it has this 3 rows and it has 3 columns. Of course, it has 3 rows and 3 columns. So here is a 3 by 3. So it has the same number of sides, the same number of rows, and same number of columns. So a square matrix is a matrix. Okay, a square matrix contains same row and columns. So that is the definition of a square matrix. I think that is understood. Maybe I should reduce the thickness. Okay, I think it's too thin now. Okay, yeah. That's it. Okay. So let's talk about diagonal matrix. Let's talk about diagonal matrix while we save this page. Okay, talk about, so I clear the screen now. I think let's make this thing exciting. Let's pick another color. All right, so okay, let me say blue. Let's see. I'm hoping blue will work. Oops, nope. Okay. Mhm. All right. Yeah, fantastic. All right, so let's look at the diagonal matrix. So what's the meaning of diagonal? All right, when you look at a room, the diagonal is the farthest. If you look at a square or rectangular room, the diagonal is the farthest distance. Like you're taking the hypotenuse of the floor of a diagonal of a square or rectangular room. So the same thing happens in matrices. So when you're talking about diagonal matrix, okay, so I'm going to ask you an intelligence question, and of course I will provide the answer, but then I will pause. Then you check if you get it or not. All right, so a diagonal matrix is a matrix of this. So we're talking about diagonal matrix. All right, a diagonal matrix. Okay, so let's say A again. I think I'm vaccinated with A. So we have a 4, 3, 2, 1, 5, 6, 3, 2, 3. Okay, so the diagonal of this matrix, you take it from the from A11, all right? So that's the diagonal. So that's the diagonal of the matrix. That's the diagonal of the matrix. It's not diagonal matrix actually. Diagonal. Let me say diagonal of matrix. I will talk about diagonal matrix later. Diagonal of matrix. Okay, I will talk about the diagonal matrix later. All right, so that is the diagonal. Now there's something I missed out. Sorry, let me go back to it. So let's assume I don't think I really missed it out, but let's talk more about it. So 4 here is a is has location A11. All right, 5 here has location what? A22, and 3 here has location A33. Okay, so we can represent this as A11, A22. So if you want to talk arbitrarily, that's the way we represent it. So this 2 here is on the first row. So it's A on the first row and the third column. So this is A13. All right, and 6 here, this is A is on the second row, 2, 3. Okay, and just like that. So I don't want to confuse you, but then a matrix is actually defined as A. This particular matrix is defined as A equals Aij. All right, where I is everything in 1, 2, 3, and J is everything in 1, 2, 3. That's not the official way of writing it, but because you are kind of rusty, I think we should just leave it like that for now. How it is written officially, we may get to that later. So we've talked about the diagonal of matrices, the diagonals of matrices, and we have even talked about a little bit of other stuff. But then let's now go to half diagonal of matrices. So half diagonal. So every other thing that is outside the diagonal matrix is off diagonal elements of a matrix. So in this case, we know that one off diagonal. So we still know that we have one. We have no. Don't let me. Let's say this is a 2, 1. Then a. This is a 3, 1. A 3, 2. A32, and so on. Those are the of diagonal. If you look at the diagonal matrix, the diagonal elements of the matrix, you see that they are the indexes are equal. So it's 1, 1, 2, 2, 3, 3. Any other thing outside such arrangement is off diagonal. All right. So now let's talk about identity element. Okay, let's talk about the diagonal matrix particularly now. Let's talk about the diagonal matrix. So that's we have talked about diagonal of a matrix. Then the diagonal matrix, it's a matrix that contains zero off diagonal elements. Where I mean a matrix that's all the diagonal none off diagonal elements are zero. So we talk about let's say diagonal matrix now. All right. If we're talking about this now, let's take a look at this one. So we say A equals everything else is zero. So let's add the diagonal first. Let's say 2, 3, 4, but everything else is zero. Everything else is zero. Okay, that is it. So you see that this is it. Now the question I'm going to ask you is that is it possible quiz because uh, you're training to be a high uh, designer, so by now you should start testing your knowledge without not everything I teach you should be able to reason out what uh, should be. Okay, so quiz um, is okay. Remind me of square matrix. I think we did that in the last discussion. Okay, you remind me what the square matrix is. That's the first one. All right. Okay, can a, a non-square matrix be a diagonal matrix? Can a non-square matrix be diagonal? All right, let me know what's your answer to that quiz is. So I'm going to save this page now and clear the canvas. All right, so let's talk about the identity matrix. We've talked about the zero matrix, which is an all zero affair. Now we talk about the identity matrix. Identity matrix. So an identity matrix is a square matrix. Sorry, an identity matrix is a diagonal matrix. All right, but this time around, all the elements along the diagonal are one. Okay, so we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so this is so you can see that only the diagonal elements, only the diagonal elements of this matrix is non-zero. Every other thing is zero. So this is an identity matrix. This is an identity matrix. The thing about identity matrix is that when you multiply it by another matrix, it returns that other matrix back. It doesn't change what you have. That is it. That's the identity matrix. Now let's talk about the lastly on the introduction to matrices. I think this is actually like a crash course to the introduction to matrices because I want us to get to vectors as quickly as possible and discuss it. Let's talk about the transpose of a matrix. We are still coming back to matrices later. Transpose of a matrix. But I want you to see other stuff. So, well, there's a long note here about it, but I think I should skip it. Okay, let me read out the notes. Why I will not write it. I don't think it makes any sense to read it. I'll just tell you what it is. So let's say A is a matrix. From my own understanding, I think for someone to learn math better, demonstration is the key. So let's say this is a. Of course, this is A11, A2, A12, A13. This is A21, A22, A23. Okay, that is obviously a 2 by 3 matrix because it has two rows and 3 columns. Okay, now that's A. Now the transpose of A, which we normally write as AT. All right, AT. Well, now this is a 2 by 3 matrix. Then its transpose would be a 3 by 2 matrix. It's going to be a 2 by 3 matrix. So it's going to be, often what you do is that you interchange. Let me pick a color for excitement, nothing else. Okay. So what you do is that you interchange the positions of the indexes. You interchange the position of the indexes. So if it is A12, it becomes A21. Then A13 becomes A31. Of course, definitely, if you look at that, you know that the diagonals would be retained because diagonal have the indexes of the diagonals are the same: 1, 1, 2, 2, 3, 3. So even if you flip it, you are not getting anything out of it. So here it means that we are going to retain our A11 at the position where it is. Then this particular one, which is A12, becomes A21. So it means that we are coming here to say A21. This guy that is A13 will become A31. Okay? Now, this guy that is A21 becomes A12. A12. And this fellow, which is A22, you see, nothing changes. It stays where it is. And the last one, which is A23, becomes A32. All right. Then you put the brackets. That's a wobbly bracket. I'm sorry about that. Okay, so you put the bracket and you can see that now we have a new matrix which has how many rows? 3 rows: R1, R2, R3, and 2 columns: C1, C2. So it's now a 3 by 2 matrix. So that's the transpose of a matrix. That's the transpose of a matrix. Let me clear this thing. I still have some other interesting thing to tell you about the transpose of a matrix. Okay, yeah, this is my notes. Okay, there you are. Let's look at examples. We have used arbitrary variables. So let's use so let's look at an example. Let's look at the first one. So we say A equals 4, 5, 1, 3. Okay, so this is going to be. Let me change the color. Let me change the color to black. Sorry. Okay, sorry. Okay, it's not. Okay, okay, right. So I think it's red before. So let me pick this black. Okay, sorry about that. So let's see. Okay, this is a 1, 1, 1, 2. This is a 2, 1, 2, 2. So it means that A transpose will be, of course, like I said, 1, 1 will be retained. That's 4. Okay, which one will now be 1, 2? This one is 2, 1 before, so it becomes 1, 2. So 1. This one is 1, 2 before, so it becomes 2, 1. That's 5. And then the other diagonal element takes its rightful position. All right, nothing has changed. A square matrix will retain the transpose of a square matrix automatically is still going to be the same square matrix. So nothing will change about that. Only the arrangement of the elements will be different. Let's look at another example. This is going to be the last example we'll be looking at. Another example. Let's say A is a 4, 5, and 5, 3. All right. Well, A transpose is nothing, but if you look at this one, this is excuse me. Okay, so this is if you look at this one, this is 1, 1. This is 1, 1. This is 1, 2. This is 2, 1. This is 2, 2. So if you are taking the transpose, you just interchange stuff. This is going to be 4 since 1, 1 will remain as 1, 1, and this 5 will come here. So it's going to be 5. This 5 will go up there. It's going to be 5, and this place will be 3. You can see that in this case, A itself is the same thing as its own transpose. What name do you think they give that? When something balances out like that, in mathematics, it's called symmetry. So this is called a symmetric matrix. So when A equals AT, then A is a symmetric matrix. All right, so that ends our crash course on matrices. I hope you understand what you've done. Now, let's go to the main reason why we are here. Let's go to the main reason why we're here. I will now go to, okay, we are dying. I'm trying to find it in my notes. We'll now go to, okay, yes, here you are. Vectors. We'll now go to vectors. Let's go to vectors. Coming. All right, vectors. So when we started a few moments ago, you remember that I defined some matrices as like this, like A1. Like okay, let me say A1, like A, B, and C. All right, and I think there's another one that I put as A, B, and C, something like that. So this is A, and this is B. See, you can see that these elements are just columns, and okay, well, it has this particular one. How many rows will you say A has? A has 3 rows. So yes, it has 3 rows and 1 column. B has 3 columns and 1 row, but nobody talks about that. So we look at this guy A as a column, and we look at B as a row. So we call this one the column vector, and we call this B the row vector. All right. So everything you have learned about vector will come alive now. After you see, you will now be able to relate vectors. They say vector is something that has a direction and blah blah blah. That's what physics folks tell us. this time around, we are going to be looking at our vectors in terms of algebra, in terms of matrices. All right. So everything will become clear. Let's do the theory first, then you see the practicability of it. So a one row, a one column matrix is a vector. That's just, so let me write it down. So let me write it with a, because it's special, so I'm going to write it with a special pen. A one column vector, matrix is called a column vector, and a one row matrix is called a row vector. All right, so know that one. All right, so now what's of a single, this is interesting. Okay, what will you then call a single uh, element matrix? Right, something like a 3, for instance. All right, this is what physics folks will call scalar. It's nothing but just a number. It's nothing but just a number. So it's a scalar, whereas this other folk is a, this other guy here is a vector. All right, so we've talked about that. Now, um, how do we represent scalars? I mean vectors. All right. Why the other ones? So here, let's say this is a a a. All right. We know that it can be row 1, column 1, row 2, column 2. That is, it can be, this is, of course, this definitely is row 1, this is row 2, this is row 3, and this is a column 1. So this will be, this should be 1, 1, 1, and 1, 2, and 1, 3. But then nobody, okay, this is A. And the another way of putting A is by saying this is A, 1, 2, 3. You don't need to waste your time adding those other guys. Now, if you take a look at it, okay, let me ask, it's a quiz. So you go back to the note and check quiz. All right. What is the transpose of a C matrix, or of a C vector, sorry. What is the transpose of a C vector? All right, so what's going to be the transpose of a C vector, where C here is the column? So what's the transpose of a column vector? Now I'll go and deal with that. Okay, I'm clearing this canvas. Now we want to start the math, the algebra of vector. So here we go, and we call it the linear combination. The linear, let me increase. Okay, the linear combination of vectors. The linear combination of vectors. So let's say this is a vector 1. So most vectors will be column vectors. We'll be dealing with column vectors mostly. In fact, that's what, let's say this is V1 and this is V2. And this is omega vector, which is omega 1, omega 2, or W1, W2. Then we can add the 2. I'm sure we are going to check our knowledge of addition of matrices later. But then because the vector is like a primitive, is a primitive form of a matrix. it's easier to deal with that right now, and let's just move on. So we have a V equals uh, V1. I'm sorry. So V plus omega will now give us. So how to add it will be you add the corresponding elements. So V1 plus omega 1 and V2 plus omega 2. So that is the way it is. And your result will give you V plus omega, which is going to be, oh, all right, there's nothing to write. Okay, let me, so that it doesn't look like I've wasted my time, let me just say V1 plus V omega 1 V2 plus omega 2. That's a total waste of time still for them. Now, that is done. Let's do something funny. I mentioned a scalar earlier. I mentioned a scalar is a single element matrix. So let's do a scalar multiplication of a matrix of vectors. Okay, so scalar multiplication. So scalar multiplication. So let's assume that our scalar is say your scalar is alpha. Let's say alpha is your scalar. Of course, like I said, a scalar is nothing but a number. Physics will tell you is something that has weight but no direction. Is a number, as far as I'm concerned. So this is alpha. All right. So if we say, okay, let me change the color. Okay, if we say alpha now times v, okay, it's going to be alpha out here multiplying v1 v2. You can see I'm picking this. All right, you can see that I'm picking that. So it's going to give you alpha v1 alpha v2, which is going to be another matrix. It's going to be a different form of a matrix. All right, so this is going to be alpha v. All right, so and let's add some. Let's suppose that alpha equals 2, therefore then 2 v1 v2 will give you 2v1 and 2v2, give you 2v1 and 2v2. We can reverse the case by multiplying it with a negative number. Let's multiply with a negative number. Okay, save. Okay, okay. So we can say, let's say our scalar is minus 1, then minus 1 times v minus 1 now, sorry, so alpha times v, of course, you know this is v now, is going to give you alpha v, which is going to give you, sorry, alpha is 2. Let's set alpha to be, sorry, let's set alpha to be minus 1. So it's going to give us minus v1 minus v2. Okay, all these things may still be looking weird, but don't worry, just trust me. Just trust me. We are, excuse me. I'm sorry about the destruction in the transmission. I'm so sorry about that. So where are we? Okay. We want to we've talked about using a scalar to multiply matrices. So let's consider two scalars, C and W. Let's consider those two scalars. Okay, all right. And let's consider two vectors, V and omega, where let's say V equals V1, V2, and omega equals omega 1, omega 2. All right, so let's say CV will be, obviously, from what we've done earlier, that's a CV1 and CV2. And um, oh, okay, sorry. This is not omega. Let's call this one D. All right, so D omega will give us D omega 1, D omega 2. So as it is, we have two different set of vectors. So we can add them. So CV plus dw becomes CV1 plus dw1 and CV2 plus dw2. So I'm going to ask you a question quiz. Is CV plus dw a vector? Okay, answer that question. List out all the questions I'm asking you, solve them, and send the answers to me. All right, so now let's look at this in a real life. Let's say our vector V is 1, 1, and omega is 2, 3. And then let's say our C is C and our D is D. So CV would automatically become CC, and D omega will become 2D, 3D, and CV plus D omega becomes C plus 2D and C plus 3D. All right, so that is where that takes us. Finally, let's now see everything we've been talking about. Let's see everything we've been talking about. Let's see where it leads us. So this is where everything becomes really familiar and beautiful, really beautiful. Now, we are now, like I said earlier, math is better done when you can see what you're doing. So let's see what we are doing with this math that we have been dealing with all day. I'm going to select. Okay, so I'm going to construct a Cartesian plane. Don't let the big name scare you. Cartesian plane is nothing but what we use to plot our graphs. All right, so that's the origin of the Cartesian plane. All right, so I'm going to label this as -1, -2. Okay, let me make it look more exciting. Okay, I think I can use blue now. Okay, so I'm going to mark the dots like that. This is the origin. This is 1, this is 2, this is 3, this is 4, and this is +1 on the y-axis. This is 2, this is 3, and this is 4. Okay, now I'm going to now pick a red. Okay, we have picked a red now, and let's look at the first vector. Let's say it's omega equals -1, 2. All right, this goes to the x-axis, this y-axis. So this is going to be -1 here, and 2 there. So where do they, okay, so we can say at that point there, that's the point uh, 1 minus 1 comma 2, that's the coordinate of that point. And if you pick an arrow, it goes straight down like that, then that is our vector. Okay, that is our vector. All right, so you can see that you are familiar with this vector thing, only that you don't know that's what's, or you didn't know that was what you've been, playing with all along. Let's look at V. V is a 4, 2. Like I said, 4 goes to the x-axis and 2 goes to the y-axis. So 4 here, that's the x-axis, and 2 here, okay, that's the y-axis. So interestingly, it means that both of them are going to intercept at around this point. Okay, so that point is a point 4, comma 2. So I'm going to tell you the implication of all this later. All right, so that is the vector V equals 4, 2, whereas this one is V equals minus 1, 2. Now let's add the two. Let's add the two. V omega plus V will give us, this is omega, and that's the. So when we add the two, we are going to have that's minus 1 plus 4, and 2 plus 2, and it's going to give us 3 and 4. So if we have that, let's just go to x-axis here, x and y. So 3 and 3 here, and 4 here. So we come to somewhere around here. That's okay. That's perfect. That's perfect. Then we have our vector. It goes like that, comes to that place. Then we know that this is a coordinates 3, comma 4, which is the endpoint of the vector. All right. So that's the sum of the two. All right. In vectorial analysis, it's actually very obvious. This guy here that I'm tracing up, that is another V, because they are the same. They have the same, only that they are not in the same plane, but they are the same vectors. And this one, yeah. So if you use the addition law of, the parallelogram law of adding vectors, you see that is that. So let me make sure that this one doesn't look awful. Yeah. So that is that. Now, your assignment is that you should sketch. Quiz. All right, sketch the vector omega minus V1, vector V minus omega. All right, so sketch those. I would like to see your thoughts on it. So now, what is this thing? This thing is nothing but on a surface, because this is a two-dimensional surface, 2D. This is a two-dimensional surface, so the vector is on two-dimensional surface. So if you are doing machine learning, these are the instructions you give the machine. Move a point from a certain position to a certain position. But then you can't tell it to move a point. You can only tell it to move a vector from a particular point to another particular point. How do you do that? By maybe adding a scalar to it to shift it away from the very point where it is, or adding it to another vector to shift it away to another location. Now that's on a surface, on a flat surface. Let's see what it looks like in three-dimensional spaces. Let's see what it looks like in 3D. In 3D, I'm almost rounding up now. In 3D, we know that, so our vector in 3D will be V equals A, B, sorry, excuse me. Okay, A, 1, 2, 3. Okay, where this one will be the x-axis, this one will be on the y-axis, and this one will be on the z-axis. So if I'm drawing that, this requires some skills, which I know I've got. Uh, this one will be the x-axis, and then this one will be the y-axis. You make sure that they are normal to each other, that is, they are perpendicular. Then the y-axis goes up like that. So what this is telling us is that this is the length, this is the breadth, and this is the height. Okay, okay, I would design it later to become a cube so that you'll be able to see it. All right, so let's look at this vector 0, 2, 2. Okay, sorry, I think I'm encroaching into my space. So let's look at vector, let's say omega equals vector 0, 2, 2. Okay, here, 1, 2, that's on the x-axis. 1, 2, 3, that's on the y-axis. And 1, 2, that's on the z, that's on the z-axis. So you put the x first. This is the x. This is the y, and this is the z. So you put the x first where it is. That's 0 on the x-axis. This is it. This is point 0. And it's aligned with 2 on the y-axis. It means you are looking at this point. So you have this particular. Let me give it a blue. Let me give it a blue for effect. All right. So this one is like that. This one is like that. All right. Then you now align it with 2 on the y-axis. So it goes up, goes up, goes up, goes up, goes up to align with 2 on the y-axis. Okay. So it aligns with 2 on the y-axis. So this is your vector. Now, this kind of vector, if you look at it very well, let's create, because it's a 3-dimensional space, then you know that it's going to be kind of volume in a way. So you can see what I'm doing. It's really, really beautiful. I remember in the classes, I used to use the ceiling fan, show that, okay, this ceiling fan is floating in space. Okay, just accept it as it is. It's not really perfect, but then it explains. So you can see it. That's the vector floating in space. So this is it. So if you're machine learning, if you are training your machine to learn how to move stuff around in 3D, then you know that you are going to be using a vector 3D. I mean a vector of a column vector with 3 elements to do that. Well, there is a R4. I mean, sorry, vector 4, which will be like a B, C, D. Then vector n, which will be something like A1, A2, going on to AN. All right. Well, but I really strongly believe that in the real world, it all ends at R3, which is the 3-dimensional space. The class will end at this point. Your quiz creates addition and subtraction of matrices in 3D. All right. Have a good day.